Hello, good afternoon, everyone. Today we continue chapter 1, main definition or introductory thoughts on aerodynamics. Last time we were talking about flow similarity, which are the criteria of flow similarity. We saw that to have similar flows, we must have several conditions satisfied, such as similar bodies, but not just similar bodies, right? We need to have same Reynolds number of the flow and the same Mach number of the flow, as well as same angle of attack. So here we will have one example. It corresponds to example 1.5 from the book. It's a bit different because in example 1.5, Anderson used imperial units, and in this example, I'm using C units for calculation because these are main units for us. So the task is the following, that we have airplane with known parameters of flight. They are Mach number of flight 885 kilometers per hour, altitude of flight almost 12 kilometers. We know density at this altitude, we know temperature and pressure at this altitude of flight according to standard atmosphere table. This data of rho infinite, T infinite, and P infinite, you can find in Appendix D of Anderson textbook at the end of the book. The question is, if we would like to test such a body in a small wind tunnel, we need to construct a small-scale model of this airplane. This small-scale model is defined as 1 to 50, so size ratio is 50, as you can see from the screen. And we need to create some specific conditions of the flow that would correspond to same Reynolds and Mach number that we have in usual flight. One restriction for this particular wind tunnel is that we have fixed temperature of test inside wind tunnel, which can be related to some structural limitations of the wind tunnel. So it's 239.9 Kelvin. I think we can consider as 240 Kelvin. So let's have this example and calculate values of Reynolds number, Mach number, and after define same properties for the flow inside the wind tunnel. I would like to remind you that we have some assumptions. First assumption is that viscosity would be proportional to square root of temperature. Okay, and let's see if we need another. We will use. So reminding you definition of Reynolds number and Mach number. Mach number is simply, right, is velocity divided by speed of sound, and Reynolds number is velocity, size, viscosity divided, density divided by viscosity. I hope it's correct. Please let me know if you have some questions or you found some mistakes in my calculation in the comment, or you can say during my presentation as well. I will take a look on the comments, and now I can see if some comment appears. So let's have this calculation. So Mach number, Mach 1, Mach infinite should be equal to Mach 1. And Reynolds infinite should be equal to Reynolds 1. These are two conditions. Now we can have such relation. As diameter or specific length for definition of Reynolds number, we use size, like 50:1. This is size ratio. Okay, so let's see what would be simpler. Maybe we can start from Mach number definition. From infinite conditions, I will write Mach number definition as velocity infinite, okay, Mach number. I will not use subscript infinite or 1 because it should be same Mach number for both cases. M infinite divided by A infinite, and should be V1 divided by A1. We know that speed of sound is also proportional to square root of temperature. From our previous discussion is known, and in gas dynamics is elaborated such equation to prove it. So I will write that velocity infinite divided by square root of temperature infinite is V1 divided by square root of temperature 1. Temperature infinite and temperature 1 we know. So from this relation, we can see that V1 would be equal to V infinite. Okay, and then multiplied by square root of T1 divided by T infinite. I hope it's correct. Now, when we have all parameters known for this formula, I will just simply calculate. Just a moment, I will calculate here. $885. Okay, now first should be probably the square root. $140 I divide by 216.6, take square root and multiply by 885. $931. At least from my calculation, I received this value. 930. Okay, to round 932 meters per second. This is the velocity of test inside the wind tunnel. You see that when we consider Mach number, it's not important how much you scale this body, because scale of the body did not enter inside calculation of testing velocity. So if you would like to keep same value of Mach, you need even to increase velocity inside the wind tunnel with respect to real flight, because temperature is is bigger on the test than in the real flight. 932 meters per second. And now I would like to calculate the other parameters of flow to keep same Reynolds number. I will write my Reynolds for big body first. Okay. Okay, we'll write proportional because since we do not know size of the body, I will use it the scale of the body. So I will write proportional to velocity 1, then C infinite instead of size, so it will be 50. And sorry, it's not velocity 1, it should be velocity infinite. Density infinite, and then we divide by square root of temperature infinite. Instead of using viscosity, we use temperature infinite. And okay, this should be equal to velocity 1. We already calculated, so we will use it in our calculation. Then C1 will be equal 1 because C infinite is 50. And density, we do not know. And we also divide by square root of temperature 1 as proportionality coefficient for viscosity. Only one unknown here is density, and we will calculate right now. I will just do what I will multiply by square root of T1, and I will divide by V1 and C1. Okay, so I will write that density 1 is equal to the square root ratio of T1 by T infinite multiplied by V. Sorry, sometimes not so convenient to write here, but it's very nice. C infinite and density infinite divided by V1 and C1. This ratio, just a moment. This ratio C infinite by C1 I will use from these initial conditions here. We'll just change color to be more understandable. Okay, all other parameters we already have in numerical values. I will just need to substitute. So density 1 would be equal to square root of 240 divided by 216 by n6, and here V infinite 88550, and the density is 0.333 kilogram per meter cubic for this altitude. And we divide by 932 meters per second. C is 1, and probably that's it. Yeah, that's it. We need to see the following formula that units should be units of density. Since we have density on the left side of this formula, we need to have also density on the right side of this formula. This is how we can check our calculation. Let's see. We divide temperature by temperature, Kelvin by Kelvin here. then we divide meters per second per meters per second. Here, this proportionality coefficient is dimensionless, 50 to 1. And we have just density in the numerator of this formula. I will calculate just a moment. We will receive some value proportional to our density and proportional to scale coefficient. So it will be bigger. We can see that we have in numerator 50 and in denominator just 1. So it will be something proportional to density and approximately 50 times bigger. But also we consider change of temperature and we consider change of velocity. Just a moment, I will calculate here. Okay, I think we have a good answer. 16.6 kilogram per meter cubic. This is the answer for density we must have in our system. So from practical point of view, what does it mean for us? It means that we need to have not just high velocity inside the wind tunnel, but also high density inside this wind tunnel. And with the low temperature, if we need to have high density, it means that also high temperature. Oh, sorry, no, not temperature, high pressure. Temperature we have. So, high pressure that would correspond to this high density. As a result, we must have a wind tunnel that allows us to control not just velocity in its test section, but also to control density in its in this test section in a big range. 16.6 is approximately 16 times or more than, let's say, more than 10 times bigger than our normal ambient temperature of air. So we need significantly to increase pressure in the test section. This can be done with, for example, such kind of wind tunnel, which is called a variable density tunnel. It allows to change several parameters as temperature, pressure, and as a consequence, change of density. This equipment is extremely complex, extremely expensive, so it's quite valuable and difficult to operate. Inside part of this wind tunnel, variable density tunnel, is shown on this picture. There is a vent, a turbine that operates, that creates flow velocity, and there is a passage around the test section that allows to bypass, to circulate air. Of course, since we need to create some specific value of pressure inside, this is a hermetic structure. Such a wind tunnel is not something simple. Nowadays, there are not so many wind tunnels of this type. And in order to reduce complexity of aerodynamic tests, not to have same Mach and Reynolds kept in the test section, it is possible to test separately with the different values of Mach number and to test separately with different values of Reynolds number, keeping just one parameter constant. For example, for big and small model, we keep Mach number of test, and for another test, we keep Reynolds number for this test. It requires less much expensive wind tunnel and can reduce total cost of development of aerospace structure. As a disadvantage, this technique should consider some value of error associated with the not constant Mach or Reynolds number and have some kind of correction methodology of similarity theory. So as we see, as a result of application of Buckingham-Pitt theorem, we can find any aerodynamic coefficient, such as lift coefficient, drag coefficient, or moment coefficient, as a value of 3 independent parameters: Reynolds, Mach, and angle of attack. Typically, aerodynamic coefficients as a function of angle of attack are represented on figure 132. We can see that there are two parameters, and there is no momentum coefficients is another discussion. That lift coefficient is usually proportional to angle of attack, has some kind of linear proportionality, right, starting from some negative value until positive high value, relatively high value, and it has some maximum at some specific value of angle of attack. Very soon we will talk about why we can have maximum of lift coefficient. This is related to physics of flow and flow separation. When we see drag coefficient, it's usually much smaller values than lift coefficient, and it can have its minimum value usually in some small positive values of angle of attack. Some small values. You can find it for from 0 to 5 degrees, for example. It's not always until 5 degrees, but for most of the airfoils, we can find that minimum value of drag coefficient is in these limits between 0 and 5 degrees, where the lift coefficient maximum angle of attack is much higher. It can be 10, can be 15, can be 20 for some airfoils or some wings. For better wings and airfoils, from point of view of maximum values of angle of attack, this maximum angle of attack can be high. Okay, can be high, and definitely much higher than for minimum for drag coefficient. Why it's important, maximum and minimum for each function? It will be very obvious very soon when we will talk about efficiency from point of view of aerodynamics. Behavior is this. If you remember, we have already talked about definition of aerodynamic coefficient. I will write you here, for example, lift coefficient is CL is lift force divided by Q infinite C, for example, where C is S, or area of aerodynamic body, or could be diameter. In each case is different. In general, aerodynamic body requires some reference area, for example. Q infinite is dynamic pressure, which is calculated as 1/2 of density multiplied by velocity in square. And L is the lift force. This lift coefficient is not just a function of lift force, but can be represented as a function of angle of attack, for example. Looking back to this figure 132, we see that is changing the lift coefficient, okay, linearly. Smaller angle of attack, smaller lift coefficient, bigger angle of attack, bigger is the lift coefficient. When we apply it here and calculate velocity, for example, from this equation, we will see the following. Let me write you. We will use definition of velocity from dynamic pressure. This was equal to lift divided by here 2 goes here, density, velocity in square, okay, multiplied by chord or area. Chord or area. So what we see when we combine this equation with the CL function as function of angle of attack, we see that smaller CL, smaller angle of attack, this part becomes smaller, right? And it means that velocity becomes bigger, right? And vice versa, when we increase angle of attack, our CL becomes bigger, okay, goes in this direction. When CL becomes bigger, velocity, which is in the denominator of the right side of the equation, becomes smaller. So if we would like to fly with higher angle of attack, automatically our velocity is decreasing more and more and more. Minimal limit of this velocity is called stall velocity. It corresponds to maximum possible angle of attack, which is called alpha stall. Stall angle of attack. Okay, and vice versa. If we have 0 angle of attack somewhere here, we have minimal value of lift coefficient, and we have maximum value of flight velocity. So maximum value of flight velocity corresponds to close to 0 or 0 value of the angle of attack. Okay, just when we combine function of dependence of lift coefficient to angle of attack and the formula to calculate lift coefficient, we may find such dependencies. Higher angle of attack, smaller is the velocity. Not possible to keep the velocity as high as we had it in 0 angle of attack, for example, just looking to this equation. And not just because we don't want, just because we can't. Our energy of engine is limited, so we cannot produce very high thrust to keep high velocity on high angle of attack. Looking to another picture, figure 134, we may find also dependence on the drag coefficient. Same formula as we had for the lift coefficient, I can rewrite for the drag coefficient as well. Okay, let me write here. It will be, let's use this color here, that CD is drag divided by Q infinite S as well. So we write that Q infinite is 1/2 of density infinite velocity infinite n squared, and we multiply by our area. Okay, that's it. And we remember function of drag coefficient as we had in one of previous slides. This is alpha and this is CD axis. So somewhere close to 0, we have minimal value of drag coefficient, and it means that at this point we will have maximum value of our velocity, okay, which corresponds to minimal drag coefficient. When we increase to stall, we have maximum value of drag coefficient, CD maximum, and it will correspond to velocity of stall, which is minimum velocity. According to this equation, increasing coefficient, aerodynamic coefficient, we automatically decrease the velocity of light. In this case, it's more visible, I think, because drag D is a value that is acting against thrust. So we need to have thrust of the engine, power of the engine corresponding to required drag. If we have engine with constant thrust or maximum thrust that we cannot change, that value of D becomes independent on the angle of attack and just enters inside this equation as constant. So nothing depends on drag value. Here only velocity and value of drag coefficient are important to determine its dependence one from the other. There are different types of aerodynamic bodies related to drag. There are so-called high aerodynamic shape or high drag aerodynamic shapes that have higher drag, which can be optimized for some specific regime, can work well or very nice, for example, supersonic airplanes. But when you try to fly supersonic jet with the subsonic velocity, is not so well optimized for subsonic velocity and can be considered as high drag aerodynamic shape. And there are low drag aerodynamic shapes, for example, which are nicely profiled airplanes, for example, created for laminar or for long range airplanes, very efficient planners that are considered as low drag aerodynamic shapes that have much smaller values of drag. Low drag aerodynamic shapes with the same value of drag or with the same value of thrust can reach higher maximum velocity. So you can see it from this picture here. Of course, in all these conditions, I did not involve thrust yet. So, because definitely for supersonic, why supersonic airplanes fly faster? Because they have much more powerful energy unit, right? But if we compare airplanes with the same level of thrust, we will see that airplanes which are more perfect from a point of view of efficiency, they will fly definitely faster than just regular or high drag aerodynamic shapes. Main criteria of aerodynamic performance is shown on this figure 135. Is a ratio between lift and drag. Usually I ask question, okay, which aerodynamic body you consider as the best? How we can compare two different airplanes? If we can we say that one airplane from aerodynamic point of view is better than the other? And the answer is this criteria here, lift to drag criteria. It's not important if you have just high lift, but you have very high drag as well. And vice versa. It's not important to reduce just drag, to reduce just losses. You also need to have this airplane to carry some weight from some distance. So the correct criteria from aerodynamic point of view is a ratio between lift and drag. It's a ratio also between weight and thrust of your airplane, which is same. Lift to drag is same as weight to thrust for constant velocity and constant altitude flights. We have for each airplane such graphics, not just for the best, just for any type of airplane or airfoil. We can find such graphics where we can see ratio between lift and drag for various flight velocities. We can find that there is always a maximum of such flight velocity that produces maximum possible lift to drag ratio. In case of work 1, I propose you to calculate for your chosen airfoil this curve in terms of flight velocity, or maybe better in terms of angle of attack, because these quantities also can be calculated for various angles of attack. Also, we can see that exists a maximum of lift to drag ratio for any kind of airfoil or wing or complete airplane that characterizes aerodynamic efficiency of the body. Aerodynamic efficiency of the body. Usually, this maximum angle of attack of maximum lift to drag ratio is small, is between 0 and 7, 0.5, 0 to 10 maximum. For each specific airfoil or each specific wing, this value is different, but it always can be obtained numerically when you have data for lift coefficient and drag coefficient. I can also extend this here, and I can tell you that lift to drag is same as weight to thrust ratio for constant velocity and constant altitude flight. And as we may see from definition of aerodynamic coefficients, it will be also same as lift coefficient to drag coefficient ratio. So it's not important which, or you take just force, or you take aerodynamic coefficient. Ratio will be same between them, because we divide by same dynamic pressure and we divide by same area. We cancel pressure and dynamic area from both of these definitions, and we have this relation. Okay, another example here is also from Anderson book, is in imperial units. Here I translate you to C units, asking to calculate aerodynamic coefficient of lift for such airplane and the lift to drag ratio. This is very simple. Let's do quite fast, just to show you how can be calculated these parameters. So we have velocity of flight, altitude of flight, we have weight, we have density of flight on this altitude, we have drag coefficient, and we have area. This is a planar area of airplane, which is used to calculate aerodynamic coefficient. So to get the lift coefficient, we need to practically have everything, right? Let's calculate. Let's try at least. If I make some error, please write me or tell me in comment. Okay, CL is lift divided by Q infinite S, and the same as weight divided by Q infinite S. Okay, and why I make equal lift to weight? Because I have already constant altitude, so it's not accelerating in vertical direction, and it means that force of weight is equal to force of lift. Okay, I have 67 to 100, and below I have, here I have 2, density is 0.414, and velocity is 792 kilometers per hour. We need to calculate in meters per second to be all in C units. How we calculate in meters per second? We have to multiply, right? Wait. How we can do it? We divide by 3.6, probably. We divide by 3.6. 792, and my 3.6 will be here. I hope it's correct. And we forgot to write area. It's 3187. I will use 32 meter square. Multiply by 32. Let's see. I hope it will be correct. No. It's in square. It's in square. So velocity in square, right? And 3.6 also should be in square because of this. So, okay, I hope now it's better. Please check if some error appeared, let me know. And meanwhile, I will calculate. I will have 67 to 100 multiplied by 2, multiply 3.6 and 3.6, and divided by 0.414 divided by 792 2 times, and divided by 32. Do we have it? Yeah, probably. Yeah, we have. I received 0.21. This is a good value for lift coefficient. I mean good because it's not so small, not negative. It cannot be negative, right? But it can be very, very small, which usually is not possible to have for sustained flight. It must be something of realistic and cannot be high. About exactly how big or how small could be values, we will speak very, very soon. 0.21 lift coefficient and lift to drag ratio. Lift to drag ratio is CL by CD, and 0.21 divided by 0.015. Let me calculate. Zero 0.15. It's 14. Also nice value. Okay. This is lift to drag ratio. This is lift coefficient. What is asked to calculate in example 1.6. Okay. What we can say about these values? When we calculated lift to drag ratio, we can compare with some typical values for airplanes. This is can be between 10 and 20. For typical airplanes is something between 10 and 20. So we are having 15 is good. And it means that physical meaning of this 14, it means that thrust of our engine can be 14 times smaller than weight of our engine. So to fly it in these conditions, we need to divide our weight by 14, and we obtain thrust of the engine, which we need to have this flight at constant velocity and constant altitude. And that's quite acceptable. Another example that Anderson shows to calculate such aerodynamic coefficients of such aerodynamic properties is conditions on takeoff before we calculated maximum velocity. And here we calculate takeoff or stall conditions. We see that in such case, weight is higher. It means that our airplane is still full of fuel. Okay, stall velocity is much smaller than cruise velocity. The altitude is 0 meters, so we are just taking off our airplane from ground. And here is the density of the air on 0 altitude. This density you can also find in standard atmosphere table in appendix of the book. Planar area of the airplane is the same structure. So not important if we calculate the structure for high altitude flight or on the ground when it just takes off. Of course, reference area is same because this airplane has constant geometry. Okay, has constant geometry. Is asked to calculate maximum value of lift coefficient for this airplane. We can do it in the same way that we did previous calculation. We just write that CL maximum would be equal to weight, okay, maximum weight that we have on takeoff. We divide by, okay, we multiply by 2 and we multiply by density, again, velocity of stall in square and the area. I already will try to do transformation of velocity from kilometers per hour to meters per second. Please, in your calculations, do not forget to do such kind of transformation if you use some reference velocity. And I will use these numbers here, 71230. 71230 and multiplied by 2, I will divide by 123 here and 3187. And I will transform velocity to meters per second. You know this coefficient of transformation. We just needed to multiply by 1000 and divide by 3600 hours to seconds and kilometers to meters transformation. And it goes in square. Okay. Just a moment, I will calculate again this value. 71230. No, something is wrong. Okay, I need to check what I calculated wrongly here. And if you see some error in my calculation, please let me know. Some mistake of few times. Strange. Just a moment, I will try to find this error and we can continue. But if you found first, please write in the chat. Yeah, I found already. It was in my calculation. I divide 2 times by area. Receive 2 small values, smaller than previous lift coefficient. But now it's correct and is equal 1.82 approximately. I make rounding. 182. You see, it's almost 2. Okay. This is the value of maximum lift coefficient. For such case, unfortunately, we do not have some data to calculate drag coefficient and to compare lift to drag ratio in this case, but it will be smaller, much smaller than for the first case for stall flight. Because if you remember, lift to drag coefficient has such a curve. Okay, so it goes down when you increase angle of attack. It decreases. So maybe we have a much smaller, maybe 4, 5, 10, something like this. Let's see, depends. If we would have thrust of the engine at this moment, we would be capable to calculate this value, lift to drag ratio. But since we do not have thrust or we do not have drag coefficient, we cannot extract anything about it in this example. But okay, in future, I think we can have more examples. Then Anderson proposes to talk about different types of flows. I will pass quite fast that you'll know this information, and I think it's not the first time that you will hear different types of flows: free molecular flow and continuous flow, then inviscid and viscous flows, then incompressible and compressible flows definition, and Mach number regimes. This is preliminary introduction in first chapter of Anderson, because after he speaks about all these types of flows in details in further chapters, and not just about this, but also about some specific aspects concerning these chapters, but not about just one type of flow is not covered in one type of flow is not covered in aerodynamics, is free molecular flow, which is outside of continuous medium, which we do not consider as an appropriate type of flow for solution by Navier-Stokes equation or any other continuous flow method. So this is another type of flow which is not covered in this book. Aerodynamics, classical chart that is working with the continuum flow, where we cannot see separate molecules and we see just a medium with average properties. This flow, this medium can be viscous, considered as viscous and inviscid. And for both of these types of flow, it can be considered as incompressible flow or compressible flow. In this division, compressible flow also can be separated to subsonic flows, transonic flow, supersonic, and hypersonic flow, depending on a value of dimensional criteria Mach number. Okay, continuous versus molecular flow, I will not tell you, probably you already know. This is not so much interesting. At least we do not have any theory about it in aerodynamics, so I see no reason to talk about. You can study this type of flow in other subjects, for example, propulsion. We have a propulsion course which talks about engines working in the vacuum, plasma engines, right? And there is a theory of rarefied gas there. Inviscid versus viscous flow is extremely important, especially in application for aerodynamic high lift-to-drag ratio structures like airfoils, where we can see two regions with flow outside inviscid and flow near the body, which is very thin and considered as viscous, where we can take into account skin friction and forces and the energies related to interaction of body and flow. Such processes are extremely important because in many cases, especially for airfoils, most part of drag force is formed by viscosity, and this is a quantity which exists only inside the boundary layer. Okay, I had here one video, but I think now this video is not working because it's just slides. You can find lots of such videos of visualization of flow. Flow separation is a process that happens in almost all aerodynamic structures, depending on angle of attack. For small angle of attack, this is smaller effect, but for higher angle of attack, for high lift, values also increase flow separation. Flow separation is not a desirable process, but it naturally appears, right? And we need to understand how to predict, how to manage with such kind of flow. We see that almost there are no models of analytical calculation. So this is why very important become numerical simulations of separated flows and experimental methods of study of aerodynamic bodies. For decades, let's say almost for 100 years, flow separation is widely studied. There are many works on this area. And in this course, we will also try to do such a simulation. Inside work 3, you will face a problem of flow separation. You will be capable to study by yourself and to present your research about flow separation in airfoil of your choices. Extremely interesting physical phenomena, extremely important. I also would like to tell you that this semester I'm working with some students to build aerodynamic tunnel, small-scale aerodynamic tunnel, especially for visualization of flow separation. So I hope that maybe middle of this year or end of this year, we will have a structure to visualize and to study experimentally flow separation in airfoils. And if it works, one day we could have some kind of practical work to see this phenomena by our eyes. This work is not simple, not fast, but it's revised that maximum in the middle of the year this structure should be constructed. It's just for the future, for people who would like to work in flow separation. I'm telling that there is a possibility not just to simulate in our university, but also to see by eyes and analyze experiments related to flow separation. Okay. Now, such a process of flow separation or viscous and non-viscous flow can happen also in other types of aerodynamic bodies, not just airfoils, but also blunt bodies like cylinder. We will see definition of blunt body very soon. Is very interesting that, for example, drag can be a source of pressure, or can be a source of viscosity, or can be a source of both, depending on how much is influence of each of these components. Aerodynamic body can be called or streamlined body or blunt body. This will be defined very soon, just for you to understand that such structures exist, and theoretical calculation can provide also experimental effects. So we can see it from theoretical point of view and from experimental point of view, these kind of flows. Okay, compressible versus compressible flow. Compressible flow is much more complex. We will study it in gas dynamics, and I think it's stuck. The screen is stuck. Okay, let's wait a moment. Okay, it returned. We will study compressible flow in gas dynamics. Difference between incompressible and compressible flow is one more equation, at least one more equation that describes the effect of compressibility. Okay, usually it's compressibility related to derivative of density by pressure change, or it can be a function of Mach number. Why function of Mach number we also will see next semester. And often it's also included in the energy equation. Compressibility changes energy significantly or redistributes energy balance significantly. So one more equation is required to calculate compressible system with respect to incompressible system. Also more complexity, more difficult to calculate. Sometimes when we can, we consider our flow incompressible because in such way flow model is much more simple and easier to manage. But in several cases not possible. Mach number regimes, subsonic flow, you already know, right? Some flow which has values of Mach number everywhere smaller than 1. Mach number is, as we saw today, is a ratio between velocity and speed of sound. Why 0.8 here? Because if we work around airfoil, we have local increase of velocity on upper part, especially of the airfoil. And because of this local increase of velocity, we need to work initially with lower values of Mach number, not to reach Mach 1 or some supersonic Mach number on this upper edge of the airfoil. So this is why subsonic is more or less until Mach 0.8. Starting from Mach 0.8, we receive so-called transonic regime. Transonic regime, it means that can be several cases of or several regions of supersonic flow around airfoil or around any other aerodynamic structure, not just could be airfoil, could be other structures, right? We have transonic regime in two different configurations. Case upper case is when we have subsonic infinite flow and local supersonic regions. For example, you can see here supersonic region also supported by shock wave transition from the supersonic region back to subsonic region on the upper side of the airfoil, and also shock wave on the lower side of the airfoil and transition from subsonic to supersonic regime, and then transition back to subsonic regime. Is the first type of transonic flow. Second type of transonic flow is when we have initially supersonic. We have supersonic flow from Mach 1 to Mach 1.2 approximately. And near airfoil is created such a bubble of subsonic flow. This bubble is will be discussed widely in gas dynamics, why it appears. Just anticipating, I tell you that it appears because there is a reaction of the body on the flow, and when flow impacts body generates pressure waves, and these pressure waves accumulate. When they accumulate, they create pressure gradient, and flow starts to stop because it's a pressure gradient that acts against the flow. So flow starts to stop and appears such subsonic region. Then all pressure waves, they are stopped in some specific position, which forms this shock wave, bow shock wave. So bow shock wave is accumulated big number of pressure waves that were generated by body, and they go against the flow. Position of bow shock wave is extremely complex, and shape of bow shock wave we will discuss with many details in next subject in gas dynamics. It's too early now before we started to talk about compressible flow equations. And at the end of such flow, we usually can have trailing edge shock. This trailing edge shock is a shock wave which is connected to the trailing edge of aerodynamic body, and is a transition, is a sort of transition when flow leaves the body to equilibrate the pressure distribution. Such kind of natural physical equilibrium happens only through a shock wave. It always exists. It's not possible to avoid. It can make only harder or softer this kind of shock wave, but this process will exist always because we have body in the flow, and the flow reacts on the body, or body reacts on the flow, which is equivalent, let's say, equivalent. Similar things that I've discussed you. Case 1 is shown on the picture. You can see visualization by Schlieren photos of shock waves or lambda shock waves, which are connected to airfoil and also related to flow separation. Shock wave, big one, is generated by several smaller, weaker shock waves. Yeah, they're called lambda shock waves because they look like letter lambda on the upper side, on the lower side. Like they have two legs at least 2 legs. And here we see visualized flow separation, high turbulence zone, which appears because of existence of the shock wave. Shock wave disturbs a lot. It creates huge gradients of flow parameters, of thermodynamic parameters, and intensifies a lot turbulence in the flow. So it's not possible to have a very nice flow in a transonic regime. I mean, nice from point of view of lift to drag ratio. It's not good, absolutely. It's not good. So we would like to avoid such kind of process, and we cannot use conventional airfoils for such kind of flows because they have very bad performance of lift to drag coefficient in this case. And there are some special types of airfoils, which we will study also in gas dynamics in transonic flow section, and especially how to predict and how to design such airfoils for performant and efficient operation in transonic regime. This is for another course also. And supersonic flows, probably you know, everywhere should be a Mach number higher than 1. We can start from some Mach number, could be 1.2, 1.5, all depending a lot on shape of the body, because not always 1.2 is enough to have everywhere supersonic flow. And then flow passes through series of shock waves, which change significantly the flow structure. This theory of shock waves we study in deep in gas dynamics. And then flow also must pass through expansion waves. Shock waves and expansion waves, they always go together. It's not possible that we have just, for example, shock wave and we will not have expansion wave. It's physics makes or nature equilibrates everything. So shock wave increases pressure inside flow, and you know probably that far distance from this body will also have same pressure as it had before, right? For example, airplane flies. Before airplane, we had 1 atmosphere, and very far from this airplane, we also have 1 atmosphere. How it's done? If we have shock waves, it just increases pressure. No, we have another opposite process, not opposite from point of view of physics, because expansion wave has very different physics, but in sense of relaxation of the flow. Shock wave creates tension on the flow, and expansion wave relaxes flow to its initial state. And we will study both of these processes analytically. You will be capable to calculate, and I hope you will like, because models are very nice and not so difficult to use. In figure 37D, you also can see picture, Schlieren photo, that shows shock wave and expansion waves after the body. One comment here that, of course, if we have supersonic flow, it could be some region where flow is still subsonic, but these regions are small, very small with respect to global volume of calculation. Same as here, we have also subsonic regions at the end of the body. Some recirculation vortexes, high turbulence, cannot be calculated analytically, can be just simulated with very big difficulties if you want a high quality simulation, and can be tested experimentally. Can be also only studied experimentally if you want extremely high quality. And hypersonic flow, something that we will also study. There is one chapter of gas dynamics devoted to this, not in a big and long discussion. Hypersonic flows are extremely complex. There is a theory of hypersonic flow, and we have several books in the library. You will see when you open these books, you will be surprised with the quantity of mathematical and physical models that describe hypersonic flow. And we will not pay so much attention on this huge amount of models because it's a question of probably more advanced subject, but we will discuss basics of hypersonic flow. So you will know if you like this subject, you will know from where you could start studying and what to expect approximately in this section. These models of hypersonic flow, they involve not just theory of aerodynamics and gas dynamics, they also involve theory of chemistry, dissociation, and ionization, plasma physics. So this is why so much complex concept cannot be seen just in aerodynamics, and should not be seen in aerodynamics. You can see very short chapter of hypersonic flow in Anderson book. So these are types of flows I wanted to present you today. Guide map of studying aerodynamics Anderson gives. And the last thing, very important, also introduction to boundary layers. You will probably already know what is boundary layer, in Portuguese, camada limite. Right, and you studied in fluid mechanics, I'm sure that you know, just to refresh your memory, not to explain from zero, right? Boundary layer is some structure that deals with change of velocity. Change of velocity happens near the body when flow interacts with the body. It stacks on molecules of gas stuck on the body of airfoil, for example, on the wall, and velocity on the wall, VA, for example, here we can see that velocity is equal to 0 on the wall. Far from this body, velocity is equal to infinite velocity. So how this transition happens? This question is answered in theory of boundary layers. There are different types of boundary layers. At least you know that there are laminar and turbulent flows, right, which have different structures and can be described by different models. Theory of boundary layer we discuss also in gas dynamics in details. There is a chapter about laminar flow. There is a chapter about turbulent boundary layer, some models, some analytical solutions. Boundary layer is also characterized by its thickness, delta, as we may see here. This thickness says to us when at this velocity stopped to change due to influence of viscosity forces. If we draw profile of velocity, for example, like this, we will see that this thickness here is a point where velocity does not change anymore. This is profile of velocity I draw. Okay, so usually we can calculate thickness of boundary layer just by seeing gradient of velocity like dv by dn. This normal direction to the wall, right? Inside the boundary layer, this gradient will be always positive, but when we are outside of boundary layer, this dv by dn will be close to 0, almost 0. Okay, velocity still can change in the normal direction. It happens due to general flow and body interaction, but it's not so huge with respect to velocity change inside the boundary layer. Usually we have reasonable estimation of thickness of boundary layer. We say that when gradient is smaller than 5% of maximum, of its maximum or initial value, we already are outside of boundary layer. So we see which was initial gradient at point A, and then at any other point we compare with this point A gradient. When it's smaller than 5%, we cut boundary layer model. Why I'm saying boundary layer so important? Because, for example, for simulation, but ANSYS is using two different models to simulate flow. Inside the boundary layer, it uses boundary layer model with viscosity, and outside of boundary layer, it uses just viscid fluid. Program automatically decides if some calculation point is inside or outside. So it chooses between two different models. So, and I'm quite sure that since we would like to use ANSYS as advanced user, we need to understand how this choice is made. At least what are the models, how this choice is made. So this is why I tell you that we must pay attention to some aspects. Work 3, you will calculate with inclusion of boundary layer model. Okay. Not just velocity changes inside the boundary layer, but also other thermodynamic properties. For example, for incompressible, incompressible flow is just the velocity change is enough, because that's the only parameter we need to calculate. But for compressible flow, we also have change of temperature, is so-called thermal boundary layer, which does not totally correspond to velocity boundary layer. Thermal boundary layer is important because we start to have heat exchange with the wall, which changes not just the temperature distribution, but also changes velocity distribution, since viscosity proportional to gradient of velocity. Okay, I will probably add here that okay, let me yeah, viscosity is a function of temperature. Since we have heat transfer between body and flow, we have redistribution of energy. It becomes very important because it impacts not just thermal processes by itself, but also impacts on viscosity. Viscosity and shear stress, right? Shear stress, I remember now this. Tau is mu multiplied by this velocity gradient. You remember this definition of shear stress. And mu is a function of temperature. So the thermal boundary layer is related to velocity boundary layer. We will discuss about these quantities in gas dynamics. Here, just preliminary. But I hope enough information for you to start understanding at least something. This is what I already told you: thermal boundary layer and velocity boundary layer, dependence on viscosity and temperature. You can see that, for example, for air, with increase of temperature, we have increase of viscosity. Typical values are these, which we use in the normal conditions because it corresponds to more or less 15 degrees. We use 1.8 10⁻⁵ in our calculations of Reynolds number, for example. As you may see also in my other videos where I explained how to calculate Reynolds number and size of the body for simulation, I used 1.8 as a viscosity. Okay, growth of thickness of boundary layer, quite obvious. I hope you know. If something is not clear about thickness of boundary layer, please let me know. I think now it's for my opinion, information is enough. And definitely this thickness increases. We can see from experiments. Two different types of boundary layers. You also should know that depending on Reynolds number, which is calculated as a function of distance of this x coordinate, is used to calculate Reynolds number. Okay, it's called Reynolds x is equal to density, velocity, infinite, right? Density infinite, and here is this x and divided by viscosity. Okay, like this. So we see that Reynolds is directly related to coordinate of flow. And depending on this Reynolds number, we have first small values on small coordinates corresponding to laminar flow, and then increasing Reynolds number, it makes transition to turbulent flows. Okay, laminar flow thickness smaller than turbulent, boundary layer thickness. Okay, about values of this thickness, we will speak very soon, so don't worry. Just important to understand it. Okay, laminar flow is more, say, predictable and maybe friendly for aerodynamic applications, and turbulent is more chaotic and consumes much more energy, but not in all cases. Okay, I would like to see if you have some questions. Usually I finish at this moment lecture. And next time we will talk about magnitudes and variations of aerodynamic coefficients, which for my opinion must be started from fresh, right? Because it's a lot of interesting data. And on Tuesday, we can start talking about such important concept, how big should be or could be aerodynamic coefficients of momentum, lift, and drag. Please let me know if you have some questions in the chat or say by voice. I can answer your questions because we have some time. And ready to answer, please. Guilherme, no questions? Okay, thank you, but no need to tell that you have no need to say that you don't have questions. Okay, thank you, people, for at least saying that you have no questions, but I honestly expect that some questions will appear because some information, maybe not so much new for you, but from aerodynamic point of view, you will see that things are different when we compare just fluid mechanics and aerodynamics, because aerodynamics is a lot more applied science that you can use in your everyday study or your everyday research than just fluid mechanics. If there are no questions, we could finish for today and we meet next week. Tomorrow we will not have class as because we had last week. Have a nice end of the week. See you next time. I expect also questions about work one if still have something. When we finish chapter 1, I will explain you better how to do work 1. Okay, I do not forget about work 1. I would like to talk much more about it because it's important to understand the best way of presentation of aerodynamic quantities and analysis of aerodynamic quantities, which is not so much clear from a theoretical book. We need to calculate something in practice to show this. So, no questions. Thank you very much and see you next time. Goodbye.
Goodbye.
Thank you, Professor.
Goodbye.